Okay, so the objectives for the capacitor lecture today is, first of all, objective B.2.A.1. So if I can annotate quickly on here, that's this one: relate stored charge and voltage for a capacitor. So we're going to learn about a circuit element called a capacitor, and the relationship between charge and voltage is kind of defines that. So we'll see that. And then also in objective B.2.B 1 through 4. So we're going to be talking about a parallel plate capacitor specifically today. And we want to be able to describe what the electric field is inside that capacitor, related to the density of the charge on the plates, and derive an expression for the capacitance of a parallel plate capacitor. And those are all kind of, those all go together. And determine how changes in dimension will affect the value of the capacitance. And we'll talk about that briefly afterwards. All right, so those are the objectives that are covered in today's lecture on capacitance. So let's get started. All right. So a capacitor, what does it do? So it's something that that generally gets put into a circuit, and what it does is it stores electrical energy, right? For at least for some, it stores electric energy at least for some period of time. So what a capacitor is, it's a circuit element that stores electrical energy. And the way it stars it's on oppositely charged plates.
How, Mr. Marcus?
Yeah.
How would they get oppositely charged plates?
Well, you can connect, if you connect two plates to opposite ends of a battery, then
So these aren't touching the circuit.
Well, they can be, yeah. I mean, they'll end up be in a circuit, and the way that we charge them up, right? The way that we get the charge on the plates, we'll go over in detail later on.
Oh, okay.
How we charge up a capacitor, and the time it takes and all that. That'll be part of it as well. We'll get to that part of the question. But for now, we just say if we do have two plates that are oppositely charged, right? One plate has positive charge, one plate has negative charges on it, and you put them near each other, right? There's going to be electrical energy. There's energy stored in that, right? Because the positive charges want to make their way over to the negative charges. The negative charges want to make their way towards the positive charges. So there's potential there for the motion of those charges, right? So that's electrical potential energy. It's an efficient way to store electrical potential energy. All right. So that's what a capacitor is. The property of a capacitor that's most important to us. A second. Okay, I got some. What is that? Oh no, just trying to get to the waiting room. Here we go. Oh, there's everybody. All right, good. Okay. So we're storing electrical energy on opposite charged plates. That's a capacitor. So the capacitance of a capacitor, right? That's kind of the most important property of a capacitor is its capacitance. And that's the ratio of the charge on the plate to the potential difference between the plates. Let me write that down before I explain. So it's the ratio of the charge on the plates to how much potential difference we can store. So to the potential difference between the plates. And for a given voltage at a given potential, right? And usually the voltage is constant because the capacitor is connected to a battery in a circuit, and we'll see how that works later on. But for a given volt, yep.
Sorry. Can you move the paper up for a second?
Up.
I want to see a word. Thank you, mister.
So what we'll see is that for a given voltage,
All set.
good. For a given voltage, if you have more capacitance, you'll be able to store more charge, right? For every volt that you connect the capacitor up to, more capacitance means you'll store more charge. So a bigger capacitor or a higher capacitance capacitor stores more charge with every volt. The equation for capacitance that we define based on this, if we call the capacitance the ratio of the charge to the potential difference, right? That's in equation form. This says C, the capacitance is defined to be the charge on one of the plates divided by the potential difference between the two plates. All right. And what we're going to find is that the capacitance of the capacitor, it only depends on the geometry of the capacitor, so on the shape. Oops, capacitor, that's I. Sorry about the handwriting again. All right, so only the shape, only the geometry of the capacitor is going to define its capacitance. And we'll look at a few different shapes of capacitors. The most important one, and we'll see in just a moment, is the parallel plate capacitor. So two flat, plates placed near each other, one with a positive charge, one with a negative charge. We'll also see that capacitance, it's good to remember, is always positive. Right, we have a plate. We're always going to have one of the plates with positive charge, one of the plates with negative charge. Right, the charges will be equal, but we'll see that when we define capacitance, we just look at the absolute value, right? Because both of the charges have the same Q. This one happens to be positive, one's negative. So capacitance is always positive, and let's also mention the unit of capacitance is the farad. And 1 farad is just to be defined as 1 coulomb per volt. So a capacitor that if you put 1 volt of potential difference across it, if you end up with a coulomb of charge, that would be a 1 farad capacitor. And that's an extremely, extremely large capacitor. Most of the capacitors that you'll see or be using are like nanofarads or microfarads, right? Billionths or millionths of a farad. So because we know that a coulomb is an insanely large amount of charge as well. Right, so usually with the normal capacitors that we'll be seeing, if you put a volt across, if you put it in a potential difference of 1 volt, you're only going to get something like a millionth or a billionth of a coulomb charge on each plate. So next, we're going to take a look directly at the parallel plate capacitor, and we're going to figure out what the capacitance is of it. But are there any questions or comments so far? Okay, so parallel plate capacitors. And we've seen parallel plates, right, when we talk about Gauss's law, an infinitely large parallel plate, or even just a parallel plate that we're not an infinitely large charged plate, or even one that's just big enough that we're not near the edge. We use Gauss's law to figure out what the electric field near those plates are, right? So you can kind of see how we'll be able to use what we know about the electric field to figure out the potential difference between the two plates. And from there, we'll get the capacitance. All right, so what we're doing now is we're going to consider 2 plates with charge positive Q and negative Q. And they each have an area A, and we put them a distance D apart. And we want to know what is the capacitance of this, right? And this is basically any parallel plate capacitor. So if we draw a diagram, it's going to look something like this. Here's one plate, and here's another plate that's kind of near it. And we'll say this one over here, it has charge minus Q, and this one over here has charge plus Q. All right? And then just drawing them end on, right? So what we have, if you look from the side, here's their two plates. That's the distance d in between them, right? This one is the minus q, and this one's the plus q. You're looking end on. So we can figure out, first, we want to know what is the electric field in between these two plates, right? And we can tell that from the Gauss's law super example, the first one that we learned. Super example 1. The electric field between the plates, does anybody remember or can figure it out? What is E if we're between these plates?
0. Wait, sorry, no.
It's not 0.
It would just be straight across.
That's the direction. You're right. It is going to be uniform inside. It's going to be straight across. It's going to point from the positive charge to the positively charged plate to the negatively charged plate. Yep, that's right. It is. That's the direction. What about the magnitude? Do we know that?
Q over epsilon naught.
Well, that's Gauss's law itself, right? That tells us that the flux, right, through some Gaussian surface would be Q over epsilon naught. But if you remember Gauss's law super example, right, when we looked at one, we didn't have two plates there. Really, we just had one plate that had a charge Q, right? We made our Gaussian surface around the plate like this. And I'm not going to go through it all again, but what we ended up was an electric field that was equal to sigma over 2 epsilon naught. And it looked like this, right? It was uniform, and it went on either side of the plate. Right, and this was and remember sigma, where sigma is just defined to be the charge per area. Right, sigma is the charge density, so how much charge per area of the plate there is. Right, so if this doesn't look familiar, go back to Gauss's law super example 1, right? That we got this equation from making that Gaussian surface around the plate, figuring out the flux, setting the flux equal to the enclosed charge over epsilon naught. But that's what we ended up with. So we can see that, right? And if that's what the electric field looks like from a positively charged plate, right? From a negatively charged plate, it's the same, except of course the lines point inward, right? The magnitude is the same, but the electric field points towards the plate when it's negatively charged, right? Because in that case, the positively charged is going to be attracted to the negatively charged plate instead of repelled by it. So if you think about it, you can see that in between these two plates here, you're going to have a field to the right from the positively charged plate that's magnitude sigma over 2 epsilon naught. And then from this negatively charged plate here, you're also going to have a field to the right that points towards it of sigma over 2 epsilon naught. So the electric field in between the plate is just double that, right? There's a field to the right from the positively charged plate and a field to the right from the negatively charged plate. Those two add up together to give us the electric field of a magnitude just sigma over epsilon naught. And for the same reason, we can see that outside, the electric field is going to be 0, right? Because when we're over here, the positively charged plate is going to have an electric field that points away from it to the left. The negatively charged electric field has an electric field that points towards it to the right, and those cancel out, right? And the same thing happens here. So it's only inside the plates that the electric field doesn't cancel out. And we'll see that the magnitude of sigma over epsilon naught. And we know that sigma, the charge density, is just the total amount of charge Q divided by the area. Right, so we can replace that in for sigma now, because that's what we're given. We're given the total charge, we're given the area of the plate.
Mr. Marcus.
Yep.
So when we found that equation,
Yep.
that you're talking about, E is equal to charge density over two
Mhm.
epsilon naught. But that was only because we looked at both end caps of a cylinder that's
Yep.
on either side of a chart of a plate,
Right.
of a charged plate. But over here we're only looking at one side. So why? So like, why are we just pulling out that equation?
Well, so we're looking, yeah. So to get this, we did need to look at both sides of the cylinder, right? Um,
Yeah, yeah.
right. That's right.
But this time we only have to look at one side of the cylinder.
Well,
So
I'm
that
only,
would change the equation.
well, what I found, I did that to find that on the electric field that we found is valid for both sides of the plate, right? So I'm not going back and using, I didn't go back and do the super example out again to come up with this, right? So what I'm saying now is that now that when we did do that, we drew the cylinder, we look at both end caps. But now we're saying, well, now that we know that the electric field is sigma over 2 epsilon naught, everywhere near this plate, we have two plates here, right? So the results we get from one plate we can add to the results from the other plate. I didn't use Gauss's law to get this sigma over epsilon naught. I used superposition, right? I said that Gauss's law says that the electric field from this plate is going to be sigma over 2 epsilon naught here, and the electric field from this plate is going to be sigma over 2 epsilon naught here. So I just add them together to get sigma over epsilon.
Okay, okay.
If I wanted to use Gauss's law on each of these, right, I would have to make two little cylinders around each plate. But I don't need to do that again since we did that already in the lecture. Does that answer your question?
Yeah, sure. Yeah.
Maybe. Let me come back. Let me come back to that and clear it up later if I so need to.
No, but
So what we've got is also, I would say, if you look again at this section in Survey and do it, where they go through and derive this, that might clarify that. So we've got the electric field inside here, right? It has to be, at least until we get near the edges, it's going to be sigma over epsilon naught, or just Q over epsilon naught times the area. Right. So we're almost to where we can say what the capacitance is, because remember from the first page, we say capacitance is just the total charge divided by the potential difference, right? The ratio of the charge to the potential difference. So we know the electric field, so we should be able to get the potential difference, and then we can get an expression for our capacitance. Right. So the potential difference, so delta V, let's look at the magnitude of it for now. We know is minus the integral of E dot dr, right? So if we take the integral and we'll go from one plate to the other plate, right? If we integrate the dot product of the electric field with the distance, we'll get our potential difference. And this is simple to do in the case of these parallel plates, because the electric field is always uniform, and it points just to the right. So that means when we take the dot product, the electric field and the dr are going to be in the same direction. So it just becomes EDR or EDX, really, because our direction is along the x-axis. And we know the electric field is uniform. So, and again, since we're just looking at the magnitude here of the potential difference, I can even take away my minus sign there and just say it's going to be equal to the uniform electric field times the integral of dx. And that's a very easy integral to do, since we're just going this distance d, right? So the integral of dx from one plate to the other plate is just going to be d. So what we just get is E times d. All right, and that's what we've gotten this expression before in simple cases where the electric field is uniform and in the same direction as the path we're integrating. So what we can see here is that the potential difference is just E times D. So now we can quickly figure out what our capacitance is for any parallel plate capacitor. Right? We get well, we know the definition of capacitance is this, the ratio of the charge to the potential difference, which is equal to the charge over the electric field times D, which is equal to the charge over, let's see, the electric field, right, is Q over epsilon naught A. So if I'm dividing by that, I multiply by A over Q times epsilon naught, and then I still have this D here in the denominator. All right, so my Q's cancel out, which is good because we know, or we expect the capacitance not to depend on how much charge is on there. So what we end up with is capacitance is just equal to the area of the capacitor divided by the constant epsilon naught times the distance between the two. And this is the equation for a parallel plate.
Shouldn't the epsilon not be on the top?
Did I not? Yep. Yeah, I think you're right. Good call. Because yeah, absolutely. Yeah, epsilon naught times the area over D. Yeah, you're right. Good catch. So what we can see though is that for how we can increase the capacitance of a capacitor, right? If you make the area, if you make the plates bigger, that makes sense. We increase the capacitance, right? That if you make the plates bigger, you can store more charge on it at a certain voltage. The other way to increase the capacitance is to decrease the distance between them. The closer together you can get those plates, the more charge you'll actually be able to store at a given voltage. And that kind of makes sense because, you know, the closer you get those plates, the larger the force between those the larger the force of attraction is between those negative and positive charges, right? The closer together you put those charges, the greater the force. And that's going to end up with more energy being stored, right? More potential for those charges to move around afterwards. So that's the end of the lecture for today. Are there any questions or comments on any piece of that?
Could you go back to the first page? Just want to double check if everything correct.
I get it all.
Yep. Thank you, Mister. I'm all set.
Problem. Anybody else? Any questions or comments on capacitors, parallel plate capacitors?
Oh, would capacitors always be parallel, or because the name hints that there might not be like parallel capacitors?
Yeah, well, there's other configurations of plate. Yeah, there's other ways. There's other ways you could have capacitors other than parallel plates. You could have if you have two like spherical shells, right? If you could think of like one metal sphere surrounded by another metal spherical shell, and you could charge both of them, one positive and one negative, that would be a capacitor, but they're not flat plates. So they wouldn't be called, it wouldn't be a parallel plate capacitor. And really in practice, what happens is in a circuit, right, a big parallel plates are going to take up a lot of room. What happens is you kind of roll up the parallel plates into a cylinder, and that doesn't change the capacitance that much. And that's why when we see capacitors in circuits, they're usually cylindrical shaped. They're those parallel.
Oh, that makes sense.
That are rolled up. Yeah. So there's a few other configurations, but by far the most common and also the easiest to calculate with are the parallel plates.
So wouldn't the spherical ones be the most efficient?
Well, the most efficient. So it's hard. That's hard. I guess we'd have to define efficiency. If you talk about having the highest capacitance in the smallest volume, I don't really know. I don't really know that. You might be right. They might be more. You might be able to get. I don't know. We'd have to calculate it and figure it out.
There's probably like some complicated way to set them up. That's why
Yeah,
they
I
don't
mean,
do it.
the spherical one that I mentioned, that's a lot harder to build, right? It's a lot easier just to put two flat plates next to each other and roll them up than to get one metal sphere inside of a metal spherical shell and still somehow get charged to that first one. So
Yeah.
it's more efficient, but it certainly wouldn't be easier to make. Good question, though. Anybody else? Anything else regarding today's lecture?
Yeah, I have another question. It's not another question. It's the old one.
Mhm.
That's a long time ago, a little while ago.
Better
But I still don't understand how the flux. Like I know that's the equation that we got for finding the electric field in the first super example, but the example now changed. Like we're not trying to find both caps. We're only trying to find one cap.
Okay, well, so remember, I'm not sure, you might be getting confused between flux and the electric field, right? We use the idea of flux here, right? Gauss's law says that the flux is equal to the enclosed charge divided by epsilon naught, right? And in
Yes.
certain situations, such as this one, when there's a lot of symmetry, right? Usually this flux we get from the integral of the electric field with the area. But in this case, it usually simplifies down to just E times the area, right? Is the
Yes.
enclosed charge over epsilon naught. And that's what we did here, right? Except there was two of them, right? There was the one on the left and the one on the right, right? So we got two.
Yes, but that's my point. We're only looking at one side. We're not looking at two sides.
You mean over here? Well, right, but what we get though is this electric field is valid everywhere basically everywhere, right? If it's an infinitely large plate, right? So just the fact that we used both end caps to derive this, right? And after we got this, we do end up with exactly this. The electric field is sigma over 2 epsilon naught, since it's the charge divided by the area. Now we know that that's the electric field on this side and on this side of this plate.
Okay, so in the capacitor, it matters what the field is on the other side as well. It's not just what's in between.
Well, so yeah, and I kind of glossed over it when I was talking about it, but yeah, the electric field on this side of the plate would matter as well, right? I mean, but it turns out to be 0, right? Because if you take right, so this is the plus Q plate, right? Both sides, the electric field lines point away, right? And from a minus Q plate, it looks like this, right? Both sides of the minus Q plate, the electric field points towards the minus Q plate, right? So if you have two plates next to each other, right, plus Q and minus Q, right? So from this plate, the charges go away, or the electric field lines point away. That's for the positive Q plate. From the negative Q plate, the electric field lines on both sides point towards it. So like this. And actually, let me continue on, because remember, it doesn't matter how far away you go. So for the plus Q plate, these rightward arrows are still here, even on this side, right? These arrows coming from the plus Q plate are still here. And these leftward arrows, and the rightwards arrows for the minus Q plate, right? Those are still exist out here, right? So you can see that to the left of the plus Q plate, these cancel out, right? The minus Q plate is pulling towards it, but the plus Q plate is pushing away from it, so it cancels out. So the electric field is 0 outside here. And the same thing out here, right? The minus Q plate would pull a positive charge towards it, but a plus Q plate is going to push a positive charge away from it. So these arrows cancel out. So there's no electric field out here either. But inside, things are different, right? Because if you're inside here, you're being pushed away from if you're a positive charge, you're being pushed away from the positive plate, which is to the right, but you're also being pulled towards the negative plate, which is also to the right? So only inside the two plates do the field not cancel out, and they actually add up. So instead of sigma over 2 epsilon naught, we get double that, which is just sigma over epsilon.
That makes sense. Okay.
Does that make it a little clearer? Oh,
A little bit.
yeah. Okay. I'm gonna stop I'm gonna stop recording there anyway. And if you want to go into that more, we can talk about that some more. But I think looking at the book and going through it a while should kind of make that difference hopefully a little bit clearer.